Hi viewers, welcome to my class on mechanics of materials. In today's class, we will work out some of the gate questions asked in the past. Let us start with the first problem. A cantilever beam OP is connected to another beam PQ with a pin joint as shown in figure. A load of 10 kN is applied at the midpoint of PQ. What is the magnitude of bending moment in kilonewton meter at fixed end O? In these questions, I removed all the options given and worked out. So this is a cantilever beam OP, and it is connected to another beam PQ using a pin joint at P. A load of 10 kN is acting at the center of PQ. So that is at 0.5 meter from P. Now this can be detached into two beams, and we can find out the internal force acting at P. Now this if you detach, it will come as a simply supported beam and another cantilever beam. So after detaching, I'll show it here. So I have separated this pin, and this part will become a simply supported beam with a central load 10 kN, and this is a roller support, so it will exert a vertical reaction, and here again you will have a vertical reaction because this load is vertical and this is also vertical reaction, so this force is also going to be vertical. Now this is a force exerted by this part of the beam, that is cantilever beam. At the end it will be exerting a force upward to support this part. Without this force, this part of the beam cannot stay in equilibrium. So there should be an upward force exerted by this part of the beam at P. Now we know when a simply supported beam is subjected to a central load 10 kN, and the support should share the loads equally. So the reaction here will be 5 kN, and here again 5 kN. So this is a force exerted by the cantilever beam to support this PQ. So it's exerting 5 kN force. In turn, this will be exerting an equal and opposite force to the cantilever beam. So these are mutual action and reaction, internal forces acting. Okay. So at P, cantilever beam is exerting a 5 kN force. In turn, this simply supported beam is transmitting a force of 5 kN. Okay, this 5 kN is coming as the part of this force which is shed by the support. So that is transmitted force, and this is a reactive force. So on the cantilever beam, 5 kN load will be acting at the point P, at the hinge P. Now hinge is removed, so it is a cantilever beam, and this is a free end and subjected to 5 kN load. Now this 5 kN will produce a bending moment at point O, and that can be calculated as 5 into 2, 10 kN meter. So at O, this will be producing a bending moment of 10 kN meter. So from right side, if you take 5 into 2, 10 kN meter is the bending moment acting at point O. Or if you work out from left side, you need to find out the resisting moment here. Resisting moment you can find out by doing the moment summation. So taking the moment summation with respect to this fixed end O, minus m, assumed an anti-clockwise couple, minus m plus 5 into 2, the moment produced by this, plus 5 into 2 is equal to 0, or m is equal to 10 kN meter. Resisting moment is 10 kN meter. So if you draw the bending moment diagram for these two beams, it's not required, but this also will come like this. So maximum bending moment will be acting at the center, and that will be 5 into 0.5, 2.5 kN meter. So it's a bending moment diagram for this simply supported beam. And if you draw it for a cantilever beam, here we have got the value of m. M is 10 kN meter. So if you take a section immediately right of O, you will get minus m or minus 10 kN meter. So that is a bending moment here, and the right end it will be 0. Okay. So this is a bending moment diagram, and the bending moment at O, the fixed end, is going to be 10 kilonewton meter. So we get the magnitude of bending moment as 10 kilonewton meter. So it's negative, but its negative is only a sign convention. So we need a magnitude of the bending moment as 10 kilonewton meter. So that is a bending moment at the fixed end of this cantilever. Okay. Let us work out another question. For the overhanging beam shown in figure, what is the magnitude of maximum bending moment in kilonewton meter? So it's a overhanging beam with a UDL of intensity 10 kilonewton per meter and 20 kilonewton load at C. Now let us take the moment summation with respect to point A and find out the reaction at B. So taking the moment summation with respect to point A, this resultant load is 10 into 4, 40, 10 into 4, and that will produce a moment of 10 into 4 into 2. The distance of centroid of the load is 2 meters away from the support. So 10 into 4 into 2 is the moment produced by this load, minus Rp into 4, the distance is 4. This will produce a clockwise moment. So 20 into the distance is 6. So 20 into 6 is equal to 0. That's the moment summation. From this you get Rb as 50 kilonewton. So reaction at B is 50 kilonewton. Now you can find out the Ra as total downward load minus Rp. Total downward load is 10 into 4, 40. This UDL is 40 plus 20, 60. Total downward load is 60. Out of this, support B is sharing 50 kilonewton. Okay. So remaining 10 kilonewton is the reaction at A. So reaction at A is 10 kilonewton. So we got the reactions at A and B. At A we have 10 kilonewton and at B 50 kilonewton. Now let us draw the shear force diagram for this. First we will calculate the shear force. Shear force immediately right of A is going to be 10 kilonewton. Okay, immediately right of A without considering this UDL. Okay, negligible part of UDL is acting. So immediately right of A, 10 kilonewton is the shear force. When you move to the left of B, 10 minus this total UDL, that is 40. So you get minus 30 as the shear force immediately left of B. Then for the section BC, it is going to be 20 kilonewton. That is 10 minus 30 plus 50. That will give the shear force in the section BC, and that is 20 kilonewton. So we got the shear force at various points. In the section AB, it varies from 10 at the left end to minus 30. So 10 to minus 30 linear variation, and in the section BC it is going to be a constant 20 kilonewton. And bending moment also we can calculate. Bending moment at A is 0. Bending moment at B is 10 into 4. That is moment produced by this 10 into 4 clockwise moment. So plus, and this is 10 into 4, 40 resultant load. 10 into 4 is the resultant load into 2 meter. It resultant load acts 2 meter away, and it's producing a negative moment. So minus 10 into 4 into 2. So the resultant bending moment will be minus 40 kilonewton meter. So at B is minus 40 kilonewton meter, and bending moment at C is 0. So we got the bending moment and shear force at all required points. We will draw the shear force and bending moment diagram. Shear force is varying in this section from 10 to minus 30, and for this section it is constant 20 kilonewton. And now you can draw the bending moment diagram. 0, and here we have calculated as minus 40, and the variation we know is parabolic, and we have a peak here because shear force is changing its sign. The diagram is required to check whether this peak is greater than 40. We know the bending moment at B is 40, and bending moment at A and C is 0. But here shear force diagram, because UDL is acting and UDL will change the shear force continuously, so somewhere the shear force may come to 0, and if a shear force changes its sign, then you are expecting a peak for bending moment, and that bending moment can be maximum, and that can be greater than this 40 kilonewton meter. So that is only idea to check this. It can be greater than 40 also. In some cases this peak can be greater than 40, and that will give the maximum bending moment. In the option list, if 40 kilonewton is there and all other values are less than 40, you can select 40 kilonewton immediately, because we know by seeing this beam you can immediately find out at B the bending moment is 20 into 2, 40 kilonewton meter. So at B it's going to be 40 kilonewton meter. From right side, if you see 20 into 2, 40 kilonewton meter is a bending moment at B. Right side clockwise is negative, so that is a sign convention. When quickly, if you have to find out the solution from right side, you can check 20 into 2, 40 instead of checking from left side, because left side you need to find out even the reactions to get the bending moment at B. But from right side, in this case, you can immediately check 20 into 2, 40 as the bending moment. But clockwise is negative, but we need to only find out the magnitude. So 40 kilonewton meter. If all other options are less than 40, immediately you can mark 40 as the maximum bending moment. In this case, let us find out this peak value. To find out the peak value, shear force is varying from 10 to 30. So 10 is here and 30 is here. Since it's a straight line variation, so it has to divide this distance in the ratio 1:3, because 10 is to 30 is 1:3. So 1:3 is the division. So totally 4 meter is there. 4 meter if you divide in the 1:3 range. So 4 divided by 1 plus 3, that is one part. We want to divide this distance also in the ratio 1:3, because shear force proportion is 10 is to 30 or 1:3. This distance also you can divide in the ratio 1:3. So to divide this into 1:3, 4 divided by 1 plus 3 or 4 by 4, 1 meter is 1 part. So 1 part is 1 meter, 3 part is 3 meter. So you get 1 part, here it is 1 part, and here it is 3 part, that is 3 meter. So it will divide the distance in the proportion 1 meter and 3 meter. So once you get this distance, you can find out the bending moment here using the area method. 10 into 1 divided by 2, area of this triangle, that will be the bending moment here. 10 into 1 by 2, that is 5 kilonewton meter. So it is less than 40, because we are not checking the sign, we are only checking the magnitude, and 40 kilonewton meter is the maximum bending moment. Let us work out the next example. A massless beam has a loading pattern as shown in the figure. The beam is rectangular cross section with a width of 30 mm and height of 100 mm. At what location the maximum bending moment occurs? Now it is subjected to UDL of intensity 3000 Newton per meter, and it's a simply supported beam with a total span 2000 plus 2000, 4000 mm. Let us find out the reactions here. Now instead of this Newton per meter, we can work out as kilonewton per meter. So it's 3000 means 3 kilonewton per meter. Okay, 3 kilonewton per meter. Instead of mm, you can take it as in meters. So it's 2 meter and 2 meter. So if you take the moment summation with respect to A, 3 into 2, that is a resultant load, into the distance is 2 plus 1, the centroid of this load. So it's 2 plus 1, that is 3. 3 into 2 into 3, that is the moment produced by this UDL. minus this reaction will produce negative moment. So minus RC into 4 is equal to 0. So RC will get as 4.5 kilonewton, and RA you can find out the total load, that is 3 into 2, 6 kilonewton minus RC, that is 1.5 kilonewton. So RA is 1.5 kilonewton, RC is 4.5 kilonewton. So after getting the reactions, we can find out the shear force and bending moment. So 1.5 is the reaction here. So in this section the shear force is 1.5 kilonewton. Shear force is 1.5 kilonewton. Here immediately right of B it is going to be 1.5 because there is only one force, 1.5 kilonewton. And here immediately left of C, 1.5 minus this total UDL, that is 1.5 minus 6, you will get minus 4.5. So in this section it is varying from 1.5 to minus 4.5. So for this section it is constant 1.5, and for this section it is varying from 1.5 to minus 4.5. So this is a shear force diagram. And again you have a change of sign for shear force under this UDL, and here you can expect a peak. Now we have to find out at what location the maximum bending moment occurs. So this distance you should find out at what location in this maximum bending moment, peak bending moment. We are not interested in the peak bending moment, but you need to find out the distance. To find out the distance, this shear force here is 1.5, here it is 4.5. These two are similar triangles. So this 1.5 is to 4.5 is 1:3. So shear force is in the proportion 1:3. So this ratio of this shear force is 1:3. So ratio of these portions will be again in the form of 1:3. So total distance is 2 meter, and it has to divide into 1 plus 3, 4 parts. This distance also will be divided in the proportion 1:3. So 1 plus 3 is 4. Divide the total distance 2 meter by 4. That will give the distance of one part. So 2 divided by 4 will give 0.5. So 0.5 is 1 part, and 3 part is 1.5 meter. So 2 meter is divided into 4 parts. One part is this, and 3 part has to come here because shear force is in the proportion 1:3. This 1.5 kilonewton is 4.5 kilonewton. 1.5 into 3 is 4.5. So it is in the proportion 1:3. So this also distance also will be in the proportion 1:3. So after getting this 0.5 meter, this already we know this is 2 meter and this 0.5 meter. So 2.5 meter is the location of peak bending moment, or 2500 mm. So we got the location of peak bending moment or maximum bending moment, and that is the required answer, 2500. So 2500 from end A. If the options are less than 2000, then immediately you can neglect. Anything which is greater than 2000 can be taken. If only one answer is there between 2000 and 4000, that can be taken as the location of maximum bending moment, because the maximum bending moment cannot occur from 0 to 2000. It has to occur either at 2000 or after 2000. So 2500 mm is the location of maximum bending moment. If you draw the bending moment diagram, you will get like this. If a question is asked to find out the peak value of bending moment, you need to calculate. So how do you calculate it? 1.5 into this 3 kilonewton meter is the bending moment here. Okay, area of this shear force diagram, 1.5 into 2. So that will give the bending moment here. And bending moment at peak point is this area also you should add. And this area is 1.5 into 0.5 divided by 2, that is 0.375. So 3, this area is 3 plus 0.375. you get the bending moment as 3.375. So peak bending moment is 3.375 kilonewton meter. But we need only this distance, 2500 mm, location of peak bending moment. Let us work out another example. In a simply supported beam loaded as shown below, what is the maximum bending moment in Newton meter? So it is loaded like this. 100 Newton is acting on an extension of the beam. So beam is supported at these points, at the ends. At the center 500 mm this extension is connected, and at 100 mm distance away from the midpoint from the center, 100 mm away from the center, this force is acting, 100 Newton is acting. You can move this force to this location. When you move it, it will also produce a couple here. So this force, the effect of this force is, this will exert the same amount of force, 100 Newton, along with the moment. So 100 into 100, that will be the moment exerted by this force. So you can transmit, you can move the force to this point and draw them. So if I move the force here, 100 Newton is acting on the beam at the midpoint, and along with the couple, that is 100 into 100, that is 10,000 Newton mm. Now you can calculate the reactions. If you are to find out the reactions, let us take this reaction as R1 and this as R2. Moment summation will give 100 into 500 plus 10,000 minus R2 into 1000 is equal to 0. So R2 will get as 60 Newton. So R2 is taking 60 Newton, and this support R1, since the total downward load is 100 Newton, support R2 is taking 60 Newton, this will take 40 Newton, remaining load 40 Newton. So you got the reactions. Now let us draw the bending moment diagram for this. Directly we can draw the bending moment diagram. At the left end the bending moment is 0, and here it is bending moment is 40 into 500, so that is 20,000 Newton mm. That is the bending moment immediately left of this midpoint, so 20,000 Newton mm. And at this midpoint, due to this couple, bending moment will suddenly change. Bending moment will suddenly change, increase by 10,000 Newton mm. It will increase by 10,000 Newton mm. So due to this couple, it will increase by 10,000. So bending moment will increase to 30,000 Newton mm, and then right end it will be 0. So 30,000 to 0. So peak bending moment is going to be 30,000 Newton mm. So that is a peak bending moment. So maximum bending moment is 30,000 Newton mm or 30 Newton meter. 30,000 Newton mm is 30 Newton meter. Let us work out another question. A concentrated load P acts on a simply supported beam of span L at a distance L by 3 from the left support. What is the bending moment at the point of application of the load? Now P is the load acting at a distance of L by 3. Now on a simply supported beam, a point load acts. The reactions at the supports is proportional to the distance between that load and the other support. So if distance is less, more reactions will be acting here. So this distance is less, so here you will have more reaction, and this reaction is proportional to this distance, and the reaction at the other end is going to be proportional to this distance. Now this length is divided in the ratio 1:2. This is one part. So this L by 3. So that is total is L. This is L by 3. So this distance is going to be 2/3 of L. So distance is divided in the proportion 1:2. The distance is divided in the proportion 1:2. So the loads will be sharing in the proportion 2:1. 2:1, and this will be two parts of this load, and this will be one part of this load. So if you divide this into 3 parts, one part is P by 3, so 2 part is 2 by 3 P. 2 by 3 P is the 2 part of the load, and one part of the load is P by 3. So the reactions will be 2/3 of P here and 1/3 of P here. So the reaction is 2/3 of P, here it is 1/3 of P, and you can find out the peak bending moment as 2/3 of P into L by 3. 2 by 3 P into L by 3, that is 2 PL by 9. That is the bending moment here. You can find out the bending moment at P. Maximum bending moment will be here at B. Maximum bending moment is at the point of application of this load, and you can find out the maximum bending moment as 2 by 3 P into L by 3, or 2 by 9 of PL, or 2 PL by 9. That is the maximum bending moment acting on this beam. So let us work out the next question. The bending moment diagram for a beam is given below. Find the shear force at sections A dash and B dash respectively. So at A dash and B dash, you have to find out the shear force. So this is a bending moment diagram. Now when bending moment is constant at any location, the shear force has to be 0. Rate of change of bending moment is shear force. So bending moment is not changing, so that means shear force for this part from this point to this point has to be 0. There will not be any shear force. Rate of change of bending moment is shear force. So bending moment is not changing, shear force has to be 0 for this section. And here for at section BB, you need to find out the shear force. It is at a distance of 1 meter from here. Now again you can apply that equation which you know, rate of change of bending moment is shear force. So here dm by dx you should find out. So to find out the rate of change of bending moment, that is slope of this line. To find out the slope of this line, you can draw a horizontal line here. So I will show it here. Draw a horizontal line here. So this is 100 kilonewton meter. So it's 100, overall is 200, so remaining is going to be 100. So 100 kilonewton meter divided by this distance is 2 meter, total is 2 meter. So 100 by 2, that is 50 kilonewton is the slope. So 100 divided by 2, 50 is the slope, 50 kilonewton. That is the rate of change of bending moment. 100 kilonewton meter divided by 2 meter, so will give 50 kilonewton. So slope of this is 50 kilonewton, and anywhere you take, not only at this particular location 1 meter away, anywhere in this section the slope is going to be same, and shear force is going to be constant from here to this point. So from this point to that end, the shear force is going to be constant, and it's going to be 50 kilonewton. So at section A you have 0 shear force, and section BB you have 50 kilonewton. So shear force diagram will be 0 here and constant value 50 kilonewton for this part. So option is 0 and 50 kilonewton. Let us work out another question. The shear force diagram of a loaded beam is shown in the following figure. Find the maximum bending moment of the beam. So maximum bending moment has to occur here. Here is the variation for shear force. Shear force is changing its sign. So maximum peak point should come here. There should be a point load here. So there you should have a peak value of bending moment. These are going to be supports. Now to calculate the bending moment here, you can go for area method. You can calculate the area of this, that will give the bending moment here. Now this you can divide into two areas, one rectangle and one triangle. So I have divided this area into a rectangle and a triangle. So rectangle is having area of 2 kilonewton into 2 meter. So that is 4 kilonewton meter. So this area is A2 is 4 kilonewton meter, and another area is so I divided this total 14 kilonewton into, after drawing this horizontal line, this will be 2 kilonewton. So 14 kilonewton is divided into 2 and 12. A triangle this side is 12 kilonewton. So you have a triangle A1 and this rectangle A2. A2 area is 2 into 2, 4 kilonewton meter. And triangle area is 12 into 2 divided by 2, that is 12. So this area of triangle is 12 kilonewton meter. Area of rectangle is 4 kilonewton meter. So 12 plus 4, 16 kilonewton meter is the bending moment at this point. So maximum bending moment is 16 kilonewton meter. You may calculate even from right side. This area you can divide into two areas. Okay, and this is 13 kilonewton. So total is 19 kilonewton. So 13, this rectangle having size 13 and remaining is going to be 6 kilonewton. So we have a rectangle. Area of rectangle is 13 into 1. Okay, 13, and this part is 6 into 1 by 2, that is 3. So 13 plus 3, total area is going to be 16, and it's negative area, but from right side when you calculate, negative areas will create a positive bending moment. You can always calculate from left side. So you got the peak bending moment as 16 kilonewton meter. Whether you calculate from left side or right side, you will have the same value of peak bending moment. So the answer is 16 kilonewton meter. And that's all for today. Thank you for watching.